Right, so last time we were looking at continuity, and we were dealing with functions from a domain in R to the D, taking values in R to the L. And we had our definition of continuity in terms of sequences, said that if you wanted to check if f was continuous at A, then you should look at every possible sequence in your domain D which tends to the point A, and see whether the values, f of xm, which gives you a sequence in R to the L, whether that sequence of values converges to the function's value at the point A. And if that works for every possible sequence in D which converges to A, then you're continuous at A. That's the sequence definition of continuity. We'll come back to the epsilon delta one in chapter 8, because in some ways I think that one gives you a better feeling for what continuity really means. So then, of course, if you're continuous at every point of your domain, that makes you continuous. If you're not continuous and you're discontinuous, that means there's at least one point of the domain where you're discontinuous. In other words, at least one point of your domain where continuity fails. So we've talked about all the standard functions from calculus, and I mentioned coordinate projections, which are really polynomials in the coordinates. So we had these very easy polynomials in x and y, which gave you projection onto the x-coordinate, projection onto the y-coordinate, and so on. And you could draw yourself a little picture of projection onto different coordinates, if you like. That could go in this gap. But I'll assume you know what it means to project onto the various coordinates. And then we finished last time talking about functions which weren't actually defined somewhere, and the fact that for us that doesn't count as a discontinuous function because it's not a function. So that's where we finished last time. We looked at the function f of x equals 1 over x and noticed that it's not actually defined at 0. And so it doesn't, for us, qualify as a discontinuous function from R to R because it isn't even a function from R to R. And if it's not a function from R to R, you can't say that it's a discontinuous function from R to R. And that's the terminology we're using in this module. Other people may have a different method of discussion on this issue. But as I say, if it's not a function from R to R, then you can't even ask whether it's continuous or not from R to R. To fix that example, you'd have to say, well, let's give it a value at 0. It wasn't defined at 0 yet. We'll make a new function, and we'll decide what value to give it at 0, not that it's obvious what to choose. Then you can make it into a function that is defined from R to R, and then it would turn out to be discontinuous. But that's a separate issue. OK, so now we move into functions of several variables, and we're going to look at all the different ways you can approach points and see how to use that to show that functions are discontinuous, though it's rather hard to use that to show that functions are continuous. So we're going to look at how can you establish that a function is discontinuous rather easily by finding a method of approach to a particular point. And this is the kind of thing you did in calculus, so this is sort of revision. So here's an example. It's a function from R squared to R for when x and y, this is this x squared plus y squared greater than 0. That's the same as saying that x comma y is not equal to 0, 0. Because you're at the origin if and only if your distance to the origin is 0. This thing here, the x squared plus y squared, is the distance from the point to the origin. So you're at the origin if and only if that distance is 0, and otherwise that distance is great. Oh, sorry, it's the square of the distance to the origin, which will be 0 if and only if the point's at the origin. So if you're at the origin, you have to decide what value to give it, and we'll give it the value 0. That seems a reasonable thing to do, because if you come in along the x-axis or the y-axis, this function takes the value 0. If x is 0 or y is 0, then this function is 0. So if you come in horizontally or vertically, everything seems to be OK. You're approaching the value 0. But if you're coming along the line y equals x, something goes horribly wrong. So what do we see? If x equals 0, then f of xy is equal to 0. If y equals 0, then f of xy equals 0. But if y equals x equals 0, then f of xy equals 0. I'm sorry to say we're on battery power today because I left the power cable in my office. So we may see one or two of the old bugs creeping back in. If y equals x equals 0, then f of xy is 0 because that was the definition of the function. This is which example is this? This is this example at the beginning of section 7.3 for those who've just come in. So we defined that if y at the point at the origin the thing took the value 0, but if y equals x is not 0, then f of xy, well, that's 2xy over x squared plus y squared is actually equal to 1. You've got 2x squared on the top and 2x squared on the bottom, or 2y squared on the bottom, whichever, because y equals x. So what happens so if you approach the origin along the x-axis or the y-axis, the function values tend to 0 because, in fact, they are 0. Okay, let's say just tends to 0. Because it's actually equal to 0. But if you approach the origin along the line y equals x, f of xy, the values of f of xy tend to 1. So f of xy tends to 1. So different methods of approach to the origin give you different limits. The conclusion is that, in fact, the general limit as you approach the origin does not exist. In particular, f of xy does not tend to 0 as xy tends to 0, 0. And since f of 0, 0 is 0, f is discontinuous at the origin. Now, I haven't made that fully formal, because in terms of our definitions, you should now convert this into sequences. But I've decided this is sufficiently convincing that I'll accept it. If you can demonstrate some clear directions of approach that will show you've got different limits, that'll prove that the limit itself does not really exist. In order to show it's discontinuous at the origin, you only have to find one direction of approach where the values don't tend to the right value in the end. So in fact, you didn't need to check the x-axis and the y-axis to demonstrate discontinuity. Y equals x alone was already enough to show that it didn't tend to 0. Checking y equals x was already enough to show that f of xy did not tend to 0 equals f of 0, 0 as xy tends to 0, 0. So that already establishes discontinuity. But that itself, because it was approaching 1 along that line, that meant that if you only check y equals x, then you haven't proved the limit doesn't exist, because the limit could have been 1. All you've done is prove that it doesn't have limit 0 by doing that. But that would be enough to prove discontinuity. But I'll give you, as an optional extra, the method using sequences. So officially, if you want to work with the definitions from this module, you would use sequences, though I'll let you use these convincing arguments anyway. Note that the sequence 0, 1 over n tends to 0, 0 as n tends to infinity. But and f of 0, 1 over n tends to 0. That's coming in along the y-axis, where x is 0, so that's 0. That tends to 0 as n tends to infinity. But 1 over n tends to 0, 0 as well. And that one's coming in along y equals x. So f of 1 over n is equal to 1 from above, which tends to 1 as n tends to infinity. So this again shows two different ways to approach the origin, giving different limits. Thus, limit xy tends to 0, 0 of f of xy does not exist. And so on. And that's how to do it with sequences. You don't have to. If you've got a convincing direction of approach to the origin, you can use that. Right, so sometimes you can't do it with straight lines. Sometimes you have to do it along a curve. Sorry, did anybody need more time on that? Yeah, I'll just bring that back. Yeah, sometimes you can't do it on a straight line. Sometimes you have to come along a curve, and you have to figure out which curve is a good one to come in along to give you some problems with the function values. And that's what the next example is about. Before we get there, let me notice that when you came in horizontally or vertically in that example, you were okay. Now, coming in horizontally, it's a bit like partial differentiation, this. When you're doing partial differentiation, you hold one of the variables constant and you let the other one vary. Well, there's this a notion similar to partial differentiation is the notion of separate continuity, where you ask, if you fix one of the variables and let the other variable vary, do you get a continuous function? That's not quite as strong as being partially differentiable. Partially differentiable is a bit better than being separately continuous. But separate continuity means that if you fix either variable and let the other one vary, so if you approach horizontally or vertically to your point, then you're getting the right limits. But that maybe some other directions might give you trouble. So separate continuity says just look at vertical and horizontal directions of approach, or if you're in more dimensions, then you look at all approach parallel to the coordinate axes. And if you appear to be continuous, when you just restrict attention to that sort of approach, you have what's called separate continuity. That if you fix all the variables except for one and let one of the variables vary only, you get a continuous function of that variable. Whereas joint continuity is the kind of continuity we're talking about most of the time, where you let both of the variables vary and you can come in along any line or curve or indeed any sort of weird sort of sequence of points approaching the point, and you've still got to get the right limit. So joint continuity is much stronger than separate continuity. And that example we just looked at was separately continuous but not jointly continuous. Here's another one. And this example, as I said before, this is one where no matter which straight line you try, it's okay. If you try any straight line here, and you get the right limit. If you're coming along either axis, then you tend to 0, which is the right value. If you're coming along some other line, then you get something that's basically cubic on the top, and then the x squared term dominates on the bottom. And so the top ends up much smaller than the bottom. It looks like you've got a y to the 4th there, you have, but as you approach the origin along a straight line, as long as x isn't 0 on that straight line, then you'll easily show that the bottom behaves like x squared, and the top behaves like constant times x cubed, and so that gets very, very small when you get near the origin. So check any straight line, this goes wrong. But there is a curve you could try to approach the origin on. This is the sort of thing you would have done last year in calculus. Can anybody suggest a curve that you could try? Yes? Yeah, x equals y squared is a very good curve for this one. So let me note, this function is separately continuous. So no problem with horizontal or vertical approaches to a point. Well, let's say to the origin. I should observe that away from the origin, this is just a perfectly good rational function and it's continuous. If you look away from the origin, then that's a rational function of x and y, a quotient of two polynomials, and you're not divided by 0. So away from the origin, this is a really nice continuous function. The only possible problem is at the origin. And that's where you do have the problem. So no problem with horizontal or vertical approaches. In fact, all straight line approaches to the origin are fine. But the curve x equals y squared, as he said, gives trouble. I think are we just checking continuity? Yes, that's right. Okay, so we'll prove that it's discontinuous at the origin by coming in along that curve. So you have to look at non-zero values. So you shouldn't be at the origin. So suppose x equals y squared non-zero, so that xy is not at the origin. Then what do we have? G of xy is equal to xy squared over x squared plus y to the fourth, which is equal to y squared over y squared squared plus y to the fourth, which is a line you could probably miss out if you could do it in your head, which is y to the fourth over 2y to the fourth. Notice that y is not 0 here, otherwise we'd be divided by 0, and this would be wrong. That's equal to half, which does not tend to 0 as y tends to 0. So if you approach the origin along the line x equals y squared, you don't tend to 0. So this shows that g of xy does not tend to 0 as xy tends to 0, 0, because you found one direction of approach where it doesn't work. Since g of 0, 0 is 0, this shows g is discontinuous at the origin. And again, I'll just show you how you do that with sequences, since that's what our definition says at the moment. So in terms of sequences, note that we'll do 1 over n squared, 1 over n. This is x equals y squared, right? Tends to 0, 0, and then tends to infinity. But g of 1 over n squared, 1 over n, that's on the curve x equals y squared, so that's equal to a half, does not tend to 0, and then tends to infinity. And since g of 0, 0, 0 is 0, we have g is discontinuous at the origin. Any questions about either of those examples? They're sort of revision examples. I've brought in this notion of using the sequence as an alternative to the directions of approach, but I'll accept the convincing lines or curves of approach as an argument. And so far, we've been looking at ways to prove that functions are discontinuous. Proving that functions that look a bit like this are continuous is a bit harder. We're going to be doing that in the next section. So do we have any questions on these two examples before we finish off this chapter? Okay? So to finish off chapter 7 then, I just want to note that the examples we've been looking at so far have been taking values in R. They were defined on, say, R squared or something like that, but taking values in R. But at the beginning of this chapter, I wanted to talk about functions from R to the D taking values in R to the L. So why are we only looking at examples where you're taking values in R? Well, the answer is that you can check the coordinates separately. The next result is about the fact that if you want to check continuity, it's enough to check each coordinate of the image separately. And if you remember what we did earlier on in this chapter, we noticed that if you had a function that did take values in, say, R cubed or R to the L or something like that, you could regard it as several different functions that took values that were real just by picking out the coordinates. So this is what we said before. We said if your function f of x is taking a value in R to the L, then you've got L different coordinates, and so you can pick out those coordinates and give yourself different functions. So, for example, if you had f of xy is equal to xy y squared, then you have f1 of xy is equal to xy, x times y, and f2 of xy is equal to y squared. You've got two coordinates, you've got two different functions in those coordinates. You can pick them out and call them f1 and f2. If you're going to R to the L, you've got L different functions, and you pick them out and you call them f1 up to fl, and you've got real valued functions. And the nice thing is that the continuity of the overall function is just dependent on whether all of those separate functions are continuous or not. So this result here, which you don't need to know the proof. There's an exercise you might want to see if you can prove it. The proof is not examinable, but you are expected to know this result and be able to apply it. In other words, if you want to check continuity, you just need to check the continuity of the different coordinates. So if you want to check that a particular function is continuous, for example, f from R to R cubed, and I'm writing down random functions again, given by f of x is equal to e to the x cos x cubed is continuous because the three functions that make it up are continuous. And again, what are f1, f2, and f3? f1 of x is equal to e to the x f2 of x equals cos x, and f3 of x equals x cubed, are all continuous. And similarly, f from r squared to r cubed defined by f of xy equals another few random functions, x plus y e to the x cubed y squared. Just move that down here. There you are. Again, that's continuous. Because each of the functions f1 of xy equals x plus y, f2 of xy, again, just because it's a function of x and y doesn't mean it has to depend on y. This one doesn't depend on y, so it's constant along vertical lines, but it's still a perfectly good function of x and y. It's not the same as the one variable function e to the x, which is only defined on the real line. F3 of xy, again, equals x cubed y squared. Each of these is continuous from r squared to r. So as long as each of the functions making up your vector function is continuous, then you end up with a continuous function. And if any of the three are discontinuous, then you get a discontinuous function. It's no good just having two continuous functions and one discontinuous one. That will give you a discontinuous function. And we've seen a few discontinuous functions already. So we know that it's possible to make discontinuous functions, even if we don't meet very many of them. And I think that brings us to the end of chapter 7. So any final questions on chapter 7 before I give you a short break, and then we can move on to chapter 8?